A street light is mounted at the top of a 20-foot tall pole. A woman 5 feet tall walks away from the pole with a speed of 2 feet per second along a straight path. How fast is the tip of her shadow moving when she is 25 feet from the pole? Okay, so we have the ground, which we're assuming is horizontal and flat. And we have the pole, which is 20 feet tall. And there's a light at the top. And then we have a woman who is 5 feet tall that is walking away from the light in a straight line along this straight path here. So the shadow is created by taking the light and drawing a straight line through the top of her head here to the ground. So this part here, the light is going to be blocked by her figure here, and that's going to make the shadow. And we want to know how fast that point is moving if we know that she is moving at a certain rate that was 2 feet per second. Okay, let's put some variables in here. Let's say that her distance from the pole is x feet, and let's say the shadow has a length of s feet. And we are given that she's moving at a rate of 2 feet per second. So dx dt is 2 feet per second. And we want to find how fast the tip of the shadow is moving. And in order to answer that question, we need to find how fast the shadow itself is lengthening. This point, this red point here, is going to be moving for two reasons. One, because she's moving, and another because the shadow itself is lengthening. So let's first find ds dt at the moment that x is 25 feet, when she's 25 feet from the pole. And then we'll add these two together, and that'll tell us how fast this point is moving. Because that point is moving because, again, it's going to be moving at a rate of at least 2 feet per second, because that's how fast she's moving. Plus, if the shadow is lengthening, that will also contribute to the speed at which this point moves. Okay, to solve this problem, we need to find a relationship between x and s, and that requires similar triangles. In this picture, we have two triangles that are similar. We have this small triangle on the right, and we have the big triangle, and they are similar triangles. And that means similar triangles, what that means is that they have equal angles. They differ only in their scale, not in their proportion. So the three angles of these two triangles are equal. Let's put that here. Here's the small triangle. This is 5. This is S. And we have some angle here. And this is a right angle. And then we have the big triangle. And this is the same exact angle. That's this angle right here. It's the same physical angle in both triangles. This side is 20. This side is x plus s. And this is a right angle as well. So we see that these two triangles have two equal angles, the right angle and the common angle. And then since the angles of a triangle always add up to 180, these two angles are also equal. So these triangles have equal angles, and therefore they are similar triangles. And the property that similar triangles have that we're going to use here is that the ratios of the corresponding sides are equal. So ratios of corresponding sides are equal. So in this context, what that means is that if we take the ratio of this bottom side here, S, to the vertical side 5, that ratio, S over 5, is going to be exactly equal to the corresponding ratio for the larger triangle, the bottom side x plus s to the vertical side 20. So this equation relates our variables, x and s, and then by differentiating both sides with respect to time, we will get a relationship between their rates of change. But before we differentiate both sides of this equation, let's see if we can find a simpler relationship between x and s. If we multiply both sides of this equation by the lowest common denominator here between 20 and 5, which is 20, then we will get rid of all the fractions. If we multiply both sides by 20, then on the left side we get 4s, because 20 divided by 5 is 4, and here we get equals x plus s, because the 20s cancel. And then we can subtract s from both sides to get 3s is equal to x. And let's express this as s, the shadow length, is x over 3. So the shadow length is going to be 1/3 the distance between her and the pole. So as x gets bigger, s, the shadow, gets longer. Let's put that in a little box. Now we'll differentiate both sides of that with respect to t. On the left side we have just ds dt, and on the right side we have 1/3 times dx dt. So the length of the shadow is moving at a constant rate of 1/3 times 2 feet per second. We were given that dx dt was 2 feet per second. So the shadow is moving at a constant rate of 2/3 of a foot per second. So it really doesn't matter how far she is from the pole, her shadow is lengthening at the same rate. So how fast is the tip of her shadow moving? The tip of the shadow is moving at a rate of 2 feet per second plus 2/3 of a foot per second. So the tip of the shadow is moving at dx dt plus ds dt. You have to add those together and you get 2 plus 2/3, or if you want, that's 8/3 of a foot per second.